Okay, YouTube, in this video we're going to look a little bit more at Gaussian elimination and matrices in order to solve a system of equations. But in the last video we kind of went through the steps of Gaussian elimination. In this video I just kind of want you to see what it looks like if you were to work through it a little bit more quickly and not talk about so much why we do the things we do. So let's go ahead and start with the fact that if we were to solve this using Gaussian elimination, we'd write an augmented matrix that would go with this system. So we'd have a 2, a 1, a 2, and I suppose this would be an 18 for our constant here in the first row. And then we have a 1, -1, 2, and 9. We also have a 1, a 2, a -1, and a 6. And so let's remember with Gaussian elimination, our goal or our effort here is to write a new, what we call row equivalent matrix, which means it has the same solutions as your original system. But instead, though, it looks like this, where we had ones down the main diagonal and we had zeros underneath any of our leading ones here. It wasn't so much we cared about what was left on the top right here as much as we wanted ones down the main diagonal and zeros elsewhere. So if our goal is to get ones down the main diagonal, let's do this first. Let's go ahead and maybe try to get a 1 in the top left corner. I think the easiest way to do this is try to switch maybe row 1 with row 2, or we could even do row 1 and row 3. How about we do row 1 and row 2? So to show my work here, and I'm going to write a little bit more small because I know that we're going to rewrite this a lot of times, I'm going to say that we're going to switch row 1 with row 2. So first things first, I always want to show my work. And I'm going to say that row 1 now is 1, -1, 2, and 9. That's got to be my new row 1. And row 2 is now what row 1 was, which was 2, 1, 2, and 18. And so row 3 we didn't affect would be the same thing as what we started with. Now using this 1 is the idea. Can we use this 1 to make everything underneath it into a 0? And so because we have a 1 there, and this is the benefit of having a 1, is that we can multiply row 1 by a scalar and then dump it onto this second row or dump it onto the third row so that when we add it onto these two values they become zeros. So the question really becomes, what could I take times 1 that when I add it to a positive 2 makes it a 0? It would be -2. Or what could I multiply by a 1 that when I add it to a positive 1 makes it 0? It would be -1. In other words, it would be the opposite of these two numbers. So respectively, we get in the habit of getting a 1 in the top left and then immediately afterwards just saying, well, you know what, I'm going to take row 1. Let me put this in red. Row 1, I'm going to take it times -2, and I'm going to add that to row 2 because that would cause this to be a 0. And I'm going to take row 1, okay, I'm going to take it times a -1 because if I take it times -1 and add it to row 3, now all of a sudden this would become a 0. So row 1, the nice thing about the fact that we have a top 1 here is that you're going to notice as we finish this, row 1 never changes anymore. Now rows 2 and 3 change, but one neat thing about it, as I can tell you right now, is these both become zeros. And just to kind of take you through this, you know, the idea is that if we were to say row 1 times a -2 and add it to row 2, that would mean that we basically, in row 1, we say -2 times 1 plus the 2 that was in the second row. You see that you get a 0. If we were to take -2 times a -1, -2 times a -1 plus now we had a 1 in the second row there, we would get a 3. So this would become a 3. If we were to take, oops, I don't want that to be red. If we were to go back and say, now let's take -2 times this 2. So we say -2 times 2 and add that on to -2 times this 2 in the top row and add that on to this entry here, which was a 2. We would get a new entry, -2. And then last but not least here, if we took -2 times our row 1 here times our 9. So we get -2 times our 9 in the first row, and we're adding that to 18. I hope you'd see that you would get a 0 there. You would get a 0. So that's kind of neat. We get a 0. Now going back and doing this now to row 3, we'd say let's take everything in row 1 times a -1 and add it to row 3. I'm going to pass on my calculator this time. I say, well, -1 times a 1 is -1 plus a positive 1 is 0. -1 times a -1 would be a positive 1, and 1 plus 2 is 3. If we were to say -1 times a positive 2 is -2, and -2 plus a -1 is -3. And then last but not least, we say -1 times a 9 is -9, and -9 plus a positive 6 is -3. So you'll notice that we get this new row equivalent matrix, but the cool thing is we've got a 1 in the top left and zeros underneath it. So now our next goal was to say, now that we have a 1 with zeros underneath it, let's get a 1 here. 1 in the second row, second column. So let's make this 3 here. I want to make this into a 1. Now here's one thing I could do. I could take the entire second equation times the reciprocal of 3, which is 1/3. But what I notice is that if I took 1/3 times 0, 3, and 0, that'd be easy, but 1/3 times this -2, it'd be kind of messy. Whereas if I were to switch now row 2 and row 3, switch them. If I took this times 1/3, everything here is a multiple of 3 or has 3 as one of its factors. So really quickly, what I'm inclined to do is say, well, then let's do this. Let's take row 2. Let's write this in red. Let's take row 2 and switch it out with row 3 here so that we just have an easier time of this. So row 1 is still row 1. Row 2 now would be what row 3 was, 0, 3, -3, -3, and then row 3 would become what row 2 was, which was 0, 3, -2, and 0. So now what we're going to do is we'll just take our entire second row times its reciprocal of its first non-zero digit here, which is this. We want to make this a 1, and anything times its reciprocal is 1. So again, row 1, still the same. Row 2 would be 1/3 times 0, 1/3 times 3, which is, I'll put that in red, a 1, 1/3 times -3, which is -1, and 1/3 times -3 is -1. And then row 3 here, we didn't do anything to it. So what we're looking at now is we had a 1, got zeros underneath it. Now we've got this, well, we switched rows to make this a little bit more convenient, but we got a 1 in the second row, second column. Now we're going to use that 1 to get rid of the 3 below it. So just as we normally would, we're going to take that 1 times the opposite of the thing we're trying to eliminate here. So we're going to take row 2, essentially, okay? We're going to take it times a -3, and we're going to add that to row 3 so that we can get rid of this 3 underneath our 1. So row 1, still the same. Row 2, check it out, still the same. Now that we have a 1 here, it's always going to stay the same. And then row 3, we definitely still have a 0 here. We're going to have a 0 here. Now let's talk about why. If we were to take -3 times this 0, it'd be 0, and then add it to this 0. This is still a 0. If we take -3 times this 1, we get -3, and -3 plus 3 is 0. Now let's take -3 times this -1. That would be a 3, and 3 plus this -2 would be a 1. And then, oh, that's kind of convenient. And then we'd say -3 times this -1 would be 3, and 3 plus 0 is 3. So when I say convenience, I say, well, because the next move would have been to get a 1 here, but since it's already a 1 here, this is in what we call REF, or row echelon form. So to rewrite our system, we would have, if we have variables x, y, and z, if we want to assume they're x, y's, and z's, we have x minus y plus 2z is 9. We would have y minus 1z is equal to -1, and we would have that z is equal to 3. So I'm going to put a box around this. I'm going to say, what I want you to know is that this original system you started with has the same solutions as this system down here. It's just that this one down here, what can I already tell you? Well, I can tell you z is already 3. I can tell you this. So we say z is 3. In terms of a solution, let's go ahead and write this here. The solution would be that, in our ordered triple, z is 3. So we could say if z is 3, let's plug this back into our second equation here, which is y minus z equals -1. Y minus z equals -1. So if z is 3, then we know y minus 3 is -1, or that y equals a positive 2, and we add that 3 to the right side. So I'll put a box around this, and that y is 2. And then we'll plug this back into our first equation for these two values here. So we'd say if x minus y plus 2z's is equal to a 9, then really x minus blank plus 2 times blank, and we'll substitute in our values here, where y is 2, z is 3. We really get x minus 2 plus 6 is 9, or that x plus 4 is 9. So in other words, we discover that x is 5 with this back substitution. So we say 5, 2, 3 is our solution to this system. And it'd be really easy to check by plugging these in for x, y, and z to all of our equations respectively to see that we satisfy all three of them. Cheers.